Okay, so this is problem number 2, and you have, imagine this like the gummy bears on skewer. So you have a 15-kilogram gummy bear skewered 2 meters away from the pivot, and a 5-kilogram gummy bear skewered 4 meters away from the pivot. So you have this big skewer, you put this stuff on it, and then you're going to grab it here, and it's going to fall down. So super quickly, there's a competition in Delaware, I think it still exists, where farmers make these big machines and they throw pumpkins. So one way to do it is the 5-kilogram thing is the pumpkin, and it's going to swing down and then go flying off tangent. Okay, so it's powered by gravity, and that's kind of the storyline. But this is really, really similar to the rotating ruler. It just giving you practice with, okay, it's not a ruler, it is blobs. Okay, so find the rotational inertia. I say blobs, meaning like gummy bears, equals the sum of all of the masses times how far they are away from the pivot. So we have a 15-kilogram blob that is 2 meters away from the pivot, and we have a 5-kilogram blob that is 4 meters away from the pivot. Okay, so I didn't spell out what these are individually, but you end up getting 140 kilogram meters squared. That is the rotational inertia of that thing. And then you can see how this is similar to the problem we just did. Find and again, I should say tangential speed, because it is not going in a line. It is flying off tangent. All right, so there's this little thing here is like a stop. So this thing swings down, that stops. That stop forces this to stop rotating, and the pumpkin has inertia, so it goes flying. All right, so what you have is, again, mass changing height. So you're going to say that TME of the first picture equals the TME of the second picture. And I like to set sea level to the lowest point. You have two options. You can find the center of mass of this 15.5 kilogram, and then you're only calculating the MGH of the single point. So it would be somewhere closer to the 15. Or we can say I have an MGH for the 15 and an MGH for the 5. It starts at rest. So it go up here. It starts at this location, boom, and then it rotates down. And so again, we're looking for omega. So the mass is changing height. You're lowering your MGH so that you have some energy for kinetic energy. Okay, so it's not moving, I guess. That's what I'm trying to say, is we only have MGH at A. At B, be really careful. The pumpkin is at sea level, but you still have the MGH of the 15. It is not at sea level. And this is a solid, if the force pivot means it's just rotating, you're forcing it to rotate about this pivot point. So you only have plus I omega squared. Okay, that's the hard part, is figuring out what kind of energy terms you have. All right, so let's just plug and chug. 15, 9.8. It is 4 meters above sea level. I hope that makes sense. Let's do this in pale green. That's where this was at the start, and that is 4 meters above sea level. Okay, and then you have the pumpkin, which is 5 times 9.8, and also 4 meters above sea level, because they're both at the same height. At point B, which is what we have here, you have the 15 kilograms at 2 meters above sea level, and you have the 1/2 I times omega squared. All right, that gives you 784 joules equals 294 joules plus 70 omega squared. It gives you an omega of 2.65 radians per second. That's how fast this device is rotating at that instant, but that's not what we care about. That's going to fling the pumpkin off tangent, and we want to know how fast the pumpkin is going. So how do you find how fast something is going? Because it is being forced to rotate. V equals omega R. So you can take 2.65, look, the units will work out, radians per second, times how far is the pumpkin from the pivot? It is 4 meters away from the pivot. And so you can see your units are going to be in meters per second. So 4 times 2.65 gives you that the tangential speed is 10.58 meters per second. Okay, if this thing had flown off instead, then its speed would be the same omega times 2 meters. So don't assume it's the thing at the end that we're always going to calculate. For whatever reason, we can make that one fly off tangent. Okay. Then just to make it interesting to see, like, would this improve the situation or not, Emil decides to modify the design. So the 15 kilogram blob is going to start here, and the pumpkin is still going to be here. But as it falls, the centrifugal force is going to send that 15 kilogram thing down towards the end. Okay, and then we're just like, is that going to make our design better or worse? So we need to find the rotational inertia at point B. We already know what it is at point A, but I at point B is going to be a little bit easier because there's only, we're going to basically say the distance is negligible here. Like, these are basically both 4 meters away. So we've got 20 kilograms that is 4 meters away from the pivot. So 320 kilogram meter squared. The rotational inertia has gone up because the 15 kilogram moved farther away from the pivot. And then I think this is the final question. Calculate the linear speed of the pumpkin and see if that's a good strategy or whether we made it worse. I suspect we made it worse because we're having this fling outward is going to slow it down. It's going to take more energy because you move the mass farther from the pivot. Okay, so we're going to still have the TME at point A equals the TME at our new point B. And the initial setup looked the same. The 15 kilogram thing started here. It's only as it moves that it slides outward. So we have the same energy. The whole system is the same. So we're just going to steal that 784 joules. We've already calculated that. So 784 joules of energy equals mgh at the bottom plus 1/2 I omega squared. These are both essentially at sea level, right? We are neglecting the width of this stuff. But in this case, yay, that makes our lives easier. These are at sea level, so I only have 1/2. Oh, I know. So he thought it might be better because now this is falling, so we don't have to deal with mgh on this side. Like, that makes it nice and easy, right? Maybe I'm going to get some energy back. But I is bigger, and I think that dominates. So I is 320, and we're looking for omega squared. Okay, so then you get omega equals 2.21 radians per second. That's not quite the final answer, but so a little bit worse, right? 2.65 turned into 2.21. Again, I think the reason he wanted to do that is because, yay, in theory, I have this 284 joules. I got more energy that I don't have to, that I can access, right? I don't have to use some of that energy for this MGH. So all 784 joules go into kinetic energy, but oh, I also made it harder to rotate, and that unfortunately made it worse. So the speed of the pumpkin is omega times r. The omega is 2.21 radians per second. How far is that pumpkin from the pivot? 4 meters. So it is now going 8.85 meters per second when it gets ejected instead of the 10.58. Okay, so sorry, bad move, but that's why you do the math, so that you know not to do that. All right, hope that makes sense. It's conservation of energy, thinking about center of mass. There's a lot of deep thinking stuff here. It's kind of abstract. So keep practicing and you'll get it.